Right.
All right.
Just
Mhm.
let me give a brief introduction on you
Yeah.
and then start. Hi, everyone. Thank you. And we're very happy to have you all here for our first talk of 2026 invited seminar series. Today, we are excited to have Shivansh Rao, who is a research engineer at Glass Imaging, and he's going to give us a presentation on AI imaging. A brief introduction about Shivansh. He leverages expertise in computer vision, signal processing, and deep learning to develop image registration and restoration algorithms for mobile imaging. Prior to Glass, he worked at Qualcomm research and development section on hardware efficient algorithms for 6 degree of freedom head pose tracking and 3D reconstruction. He earned his master's degree from Penn State and bachelor's from Delhi College of Engineering and has conducted research work at IIT Kanpur and IIT Delhi, along with collaborative research with Google AI. His research is published at CVPR, ECCV, ACM Multimedia, and other venues. And he does have multiple pending US patent applications. So with that introduction, Shivansh, please take it away.
Yeah. So good evening, everyone. I'll also give a quick intro. So my name is Shivansh, and I currently work as a research engineer at Glass Imaging. So Glass Imaging is a startup which is based out of California, and we primarily focus more on AI-powered computational photography. And thus, in today's session, I will try to share some details on the neural image signal processor pipeline, so neural ISP. So while talking on that, I will try to share some details on image registration, image restoration, and how we use these techniques to push the boundary of customer imaging. And one unique part of today's talk would be, so I like to talk about neural ISPs, not just for smartphones, but uh, branching out from smartphones to AR glasses, security cameras, drones, and beyond. Before moving forward, I would first like to thank Piraj, Upal, and the entire IEEE San Diego team for organizing this tutorial. And thank you everyone for your time. Feel free to ask questions anytime that you may have during the presentation. Uh, I'll try my best to draw comparisons between traditional ISP and neural ISP. So that will more or less be the agenda of this talk. So wherever I mention Glass AI during this presentation, I would try to refer this to the neural ISP software block that we will discuss. So Glass AI is a proprietary neural ISP software developed on the principles of computational photography. Here we try to tailor this neural ISP block not just for one phone, but instead we try to keep it uh, tailored for different camera models, different lenses, different sensors. So in some sense, our neural network is able to learn how to reverse lens aberrations that a particular lens module may have. It is able to implicitly learn what kind of sensor noise a sensor may have. And we believe this is very critical when we intend to build a neural ISP pipeline, because until our neural network is aware of the physical and optical properties of the camera, it is quite difficult for it to enhance on the image quality. So this neural ISP block, which is Glass AI, it is not a basic image enhancement software which works on top of RGB images. Instead, it is a learnable optics-based system which runs on top of noisy raw images and corrects for any aberrations and noise that that sensor raw may have. We currently work with OEMs to train and seamlessly deploy our Glass AI modes on smartphones and more recently on any camera hardware. A quick intro on the global presence of Glass. So I work from the headquarters, which is in San Mateo, California, while we also have some teams working from Tampere, Finland, which has a very big imaging community, and also a few people working from Munich, Germany. We currently partner with Qualcomm and Google in some of these developments that we have been making. So in October 2024, also in October 2025, we announced our partnership with Qualcomm, wherein we collaborated with Qualcomm's camera team to demo our application of neural ISP running real time on Qualcomm reference device QRD, supporting 8850 and 8750. So in a nutshell, if I would have to summarize what we demoed, we used the existing camera hardware from uh, the latest QRD back then in 2024. And together, after collaborating with Qualcomm, we were able to build a neural ISP pipeline, which was running on this hardware. And we were comparing the image quality with another flagship product in the market back then, which had much superior hardware and camera sensor information than the QRD. But even with a inferior hardware but more superior neural ISP pipeline, we were able to show significant benefits on the image quality. And all of this was running in real time. So for say, let's say you take out your smartphone and hit on the capture button, the entire pipeline from raw burst collection to the JPEG creation is close to 2 seconds, and the neural ISP that we have built is very efficient, so it is still able to run in the runtime efficiency, and it also has pretty good thermal throttling, ROM disk space, VRAM usage. So it's overall very efficiently designed to run on any camera within the requirements.
And also, may I ask a question?
Mm-hmm.
Also, does it
Yeah.
work for videos as well, or no? It's just
Yeah.
exclusive
So
for
I
images.
would, yeah, I would discuss it towards the end of this discussion. So we started off with photo stills as the first task, and more recently we have also kind of enlarged the scope to videos. So in October 2025, which is few months back, we had a demo again with Qualcomm on video, and the prior year in 2024 we had a demo on photo stills.
Oh, I see. Because I wanted to get an idea about what kind of
Mhm.
frame FPSs we are talking about.
So I'm not that aware of the video one because I was not involved in that project, but it was still running in. Yeah, I don't have any like number in my mind right now, but it was comparable to whatever the latest FPS is there in the market.
Okay, yeah, thanks.
Yeah, for the photo pipeline, it definitely runs in under 2 seconds end to end. So before we get started with the remaining part of technical discussion, I first wanted to show this small example wherein I want to discuss how the latest flagship smartphones still have some critical issues. So this image you're seeing here was taken with one of the flagship products. And what we tried to do was we captured the same scene at same ISO condition, just at different zoom levels. So the one on the right is wherein I'm capturing the scene on 1x zoom. And as we move left, I kind of move away from the subject, but I zoom in on the scene. So the idea here is, uh, as you zoom in on the scene, these smartphones start, like current smartphones start to use generative networks. So they start switching to their generative modeling, diffusion-based approaches. But on lower zoom levels, they rely more on restoration networks. But if you would notice, at least on this image, uh, it is supposed to be a small like black cardboard put on top of the eyebrow features. But as you start kicking in the diffusion network on higher zoom, these networks start to hallucinate so much that it starts to blend this piece of black cardboard along with the eyebrows on the leftmost. And even on the middle one, if you observe, it kind of pastes these eyebrows on top of this black piece of cardboard. And this was very surprising to us because this was with one of the most latest like flagship phones out there, and the image on the leftmost is was close to 70x native 70x digital zoom, and you would still notice it's quite sharp, and you wouldn't assume, like you wouldn't expect that much detail to be coming out of a smartphone on a 70x zoom image. So the only reason it comes out like that is because it uses diffusion networks, but then it also uh, just generates these pixels instead of restoring them. What we would be discussing in today's talk is we want to stick with the first principles of computational photography. So we are still focusing a lot on image restoration and not image generation. So we try to restore the true pixels and we would not try to generate new pixels into it. So we have cameras around us everywhere, be it from smartphones to drones to security cameras to AR glasses to professional cameras to cameras in cars and so on. But we still have we are still limited by the image quality that can be achieved with most of these devices. We are already seeing some good image quality benchmarks with smartphones, but these smartphones are still quite a bit far from what it can achieve corresponding to a professional camera. So our goal here is we should ideally achieve very high resolution image quality with each of these camera devices while reducing the like manual tuning effort and reducing the turnaround time for each of these cameras. Main issue we find here is that as we may already be aware of, each of these cameras are very different from each other. So the smartphone and the drone may have very different sensors, different optics, different CFAs, different lens modules, and we cannot keep working on individual devices with different engineering teams uh, because that would lead to very long turnaround time and it also requires a lot of investment. Thus, it essentially makes it almost impossible for a small startup or a small firm to afford the current development cycle. Bigger companies like Apple, Google, Huawei, they can still spend a lot of expenditure onto this, but still having different teams for each of these devices, having different traditional ISP approaches reduces their pace, and it also to some extent limits the scalability because we cannot keep building a different pipeline for each of these devices. Thus, we must come out of the traditional ISP procedures and we have to slowly move towards neural ISP pipelines. Therefore, our goal should be we build one common neural ISP pipeline which can be used for any of these devices. So the pipeline should be aware of the optics and the sensor details of whatever device we want the network to run on, and it should implicitly learn those characterization features of the camera, and thus still generate a decent image quality. And then from there, you could always reiterate to improve it. But the idea is we shouldn't be spending too much time on manually tuning a pipeline for individual devices. So this brings us to the core fundamentals of what this tutorial will cover. So we kind of try to bridge the gap between uh, any device with a camera to full RAW to RGB neural based ISP pipeline. We kind of break it down to two steps. And the agenda of this, I would reiterate, is we want to bring the development cycle from months of per device tuning to a learnable system that adapts itself. And by doing so, you can bring down this like months of per device tuning to just couple of weeks of tuning, which uh, which is very efficient in terms of back and forth with the customers. So we have developed this Glass AI, which is our neural ISP software, and it currently runs on the edge real time. To do this, we first uh, pick up the camera we want to work on, and we characterize the camera system in our lab. A lot of the details on how we characterize the optics of this device is part of our core IP. Once we are able to characterize the camera in our lab, we then train the network onto those characterized burst of RAWs, and we train it in a manner that the network implicitly learns for what lens aberrations it may have to correct for, what sensor noise details it may have to denoise for, and so on. Just to give a brief overview of what this RAW to RGB pipeline is. So whenever you hit capture button on your phone, or in fact any device, you will always capture a burst of RAWs. Now, how many bursts these RAWs may contain is a design decision from the manufacturer, but you would always capture a burst of different number of RAWs, let's say 8 RAWs, and these 8 RAWs would eventually be merged and restored in order to produce the final RGB output. And how these bursts are processed and restored is the proprietary algorithm for each of these OEMs. And that is also what a proprietary algorithm that Glass AI proposes here. So we have our own way of how to go from this individual sets of RAWs, characterize it, implicitly learn. So we have like physics inspired neural networks, and then eventually output the RGB based RGB JPEG. So I tried to put up a like small slide on how traditional ISP currently looks like. It has many hand-tuned blocks. So starting from the sensor, we first get the raw frames as we just discussed. Once you have the raw frames, uh, you will have a small team working on low-level correction. Once you have the raw frames corrected, like in some sense, once you have pre-processing of the raw frames done, you would have a dedicated team working on raw denoising and CFA interpolation, or the raw demosaicing team. So this team would now like denoise your input set of raws and pass that to the multi-frame alignment team. This alignment here is just image registration. So this team would essentially take in these bursts of denoised and demosaiced input images and align them with each other so that they all come to the same reference frame. And then once these are aligned to the reference frame, it is then passed to the image deghosting or image fusion team, which would try to fuse these bursts of aligned frames in an efficient manner so that you get uh, you get like the best image quality and least image artifacts. So that is what the role of this team is. Once you have this, you have the entire post-processing teams which work in different stages, starting from color space conversion. So bringing from, let's say, whatever color space the network outputs in to the color space that humans perceive these images in, to further noise filtering, tone mapping, depending on whether the user wants STR or HDR, dehazing, depending on the scene, followed by some more sharpening and detail enhancement, and so on. So what I wanted to majorly show as part of this slide was that this entire process requires per device bring up cycle. So you would have to do this entire setup for per camera that we discussed previously. And then this has very brittle heuristics. So as we can see, it has to be a sequential process between teams, and which is also prone to human error. And it also, since these teams are very like interlinked, uh, you always tune on the results coming from the output of previous team. So this has a very high risk of regressions, quality regressions, and a very long product life cycle. From our study, per device, the software life cycle here is at least 4 to 5 months, which uh, which can be uh, which can be made a lot more efficient from our experience. This legacy way of approaching traditional ISP pipeline also has a big disadvantage, as in it keeps us away from the latest research that the academia may be having. Because now, if you would have to go back and replace some blocks in this pipeline, you really need to think a lot on how that block would affect the block prior to it and the block after it. So it kind of takes us a bit away from the latest academia research and only allows us to bring incremental changes. The goal here is, oh yeah, sorry. Does someone have a question? Okay, so the goal here is we want to replace all of these red blocks by a single neural network so that you have minimal tuning blocks outside of your neural ISP. So this neural ISP block here is what we were discussing as part of camera characterization and training neural network. So most of these red blocks of denoising, demosaicing, alignment, deghosting, noise filtering, sharpening, dehazing, then cropping, upscaling, scene specific enhancements. All of that we now do as part of a single neural ISP block. So hence we move away from endlessly retuning blocks. Instead, we learn this pipeline so that it adapts to each device and it optimizes for a chosen look or chosen goal. So we still optimize this neural network training for customer requirements, but that optimization is more from training the network and not retuning the blocks. Therefore, we move away from block-wise heuristics and move closer to data-driven and goal condition optimization. One thing we were also noticing more recently was some of the flagship products also tend to change the color profile of the input images in some corner scenes, such as like more noisier images. But with the neural ISP block that we have built, since it is more inspired from physics, we tend to maintain the original color space of the input RAWs. Oh, sorry, someone had a question. Okay, so we tend to maintain the color profile of the input RAWs, whereas we notice some OEMs sometimes tend to desaturate uh, in order to hide color noise in like noisier images. So let's say if there is a very noisier image and your neural network is not uh, able to learn for the particular noise condition of that image, then it would generate some regions in the output image which may have some color noise. And in order to hide this color noise, so there are two approaches here. You could either retrain your network in a better fashion, or you could just hide this color noise by desaturating this patch. So we have seen a lot of OEMs taking the second approach. So they desaturate the color patch, because retraining your network to take care of this color noise is a more complicated task. But the way we have built this pipeline, it's more towards the first option. So we try to make it more image aware. So we make the network learn these aspects during training itself, and we do not specifically feed it during inference based on the artifacts that we see.
Yeah, I did have a question. Can you hear me?
Yeah.
Yeah. So the prior slide,
Mhm.
can you say where the errors in the image that you showed of the gentleman with the square above his eye? Can you point out where that problem happened in this pipeline, or is this not the right pipeline?
Yeah, this is still the right pipeline. So the error here, in my opinion, is somewhere in this like multi-frame fusion and deghosting part, because this is the neural network, this is the like main neural network which is responsible for image restoration. So if you replace this with a diffusion network, it would start generating details. But if you have an image restoration network here, it will not generate new details. It will just try to use these multi-frame aligned inputs and try to just merge them to give a better looking output. So it's probably happening in this block.
Okay. Did you take a picture of his eye and the square with an old optical camera?
Oh, we haven't. Yeah, we haven't tried that. But I assume if we do that, we should not see the hallucinating textures that we just saw.
Okay, yeah, that would be quite interesting to see.
Yeah. That should be very quick to check. I'll probably check that on my end, but I'm quite confident it should not have the hallucinating textures.
Right. So you'd see basically the eyeglass frame and the square is what you would see with the old style optical camera.
Yes, that's true.
Okay. Okay. Thank you.
Yeah. Okay. So continuing on what we were discussing. So how we try to solve this issue of, okay, we have so many cameras around us. How do we now start using them in a way that we can build a common pipeline to take care of each of those? So what we try to do is we try to break down these available devices as part of combination of few intricate details. But before I move to that, a very quick overview of like how a image capture process in digital cameras may look like is you have a scene or an object uh, passing the light rays through the lens. These rays falling on an image sensor, uh, and in front of an image sensor you have these CFA arrays, that is the color filter arrays, uh, and that is what I also mentioned here, like CFA types. So these color filter arrays, in simple words, it is just like a mosaic of color filters, different color filters, placed over the pixels of an image sensor. The purpose here is uh, these color filter arrays, they let each pixel capture only one color. So be it like red, green, or blue. And the reason why CFAs exist is because these image sensors, they will only measure brightness. They will not measure color. So once you place these CFA arrays on top of the image sensors, you will produce colors for each pixel, and the sensor will only capture intensity values through these CFA filters, and then you can use some demosaicing algorithm to reconstruct the full RGB image by estimating the missing values at each pixels from its neighbor. So if you have a red pixel, you just use some demosaicing algorithm for interpolation to predict for the green and blue and so on. So what we try to do is we try to break down each of these camera device as a combination of different pixel sizes. So an optical camera may have different pixel size than a more recent smartphone camera, then a drone camera, and so on. Then we categorize these into different CFA types, and CFA types, CFA patterns, and lens modules, pixel size, all of these are determined and actually designed by the OEM. Based on whatever design decisions they may have made, their camera team may have made. Some of those CFA types could be RGB, RGBW, so on. Some of the CFA patterns could be as simple as bare, raw bare CFA, or quad bare CFA, or hex CFA. And then in terms of lens modules, you may have like as you may already see in your smartphones, you will have like a ultra wide, then tele zoom, super tele, which is super high zoom, and so on. So we try to characterize our camera in a manner that our network is able to understand for, okay, for this camera, what are the different pixel sizes? What's the CFA type? What's the CFA pattern? What lens module am I currently looking at? So once the network is aware of these uh, camera relative details, it will start implicitly learning it. Now, an issue that we saw here, and also assume other camera companies or camera teams may be noticing, is that there is a lot of different variations from lens to lens. So a phone lens and a like security camera lens may have very different properties. And in fact, even within the same lens, so let's say I'm manufacturing a smartphone today, even within the same lens module, there will be a lot of manufacturing variations, and particularly for the pre-production devices. So let's say I want to launch iPhone 18 Pro in November 2026. For the camera team to start working on it, it will only have access to pre-production devices, and these pre-production devices already has a lot of lens variations. So you cannot build a network which is learned only for one particular type of lens, but you have to uh, design a network which can learn across a variety of different lens variations. And you would have to assume here what kind of variations you may see in the manufacturing facility. So this is another reason why we have to move away from traditional ISP to neural ISP, because you have to make your network aware that, okay, there may be some lenses which are faulty in your production pipeline, while there may be some lenses which are very sharp. Now you want to uh, you want to prove a very good image quality on sharp lenses, but you also don't want to degrade a lot on the faulty lenses. So the only way you can learn this variation is if you feed these variations of data in your training data, and then you make your network learn these. How you feed these variations in your training data is more on how you characterize these cameras, and that is does a very important step, like how you characterize your camera and then feed that data to your network. But in a nutshell, if you are able to characterize your camera to match very well with all types of variations you would see eventually uh, on smartphones when they're out in customers' hands, then the network should be able to implicitly learn for them. So if I would have to break down the neural ISP block into some simple steps based on our understanding until now. So for any device we have, as we already discussed several times, we characterize it in the lab, and then we will we get these set of input raw bursts, right? Which could be multiple depending on whichever OEM we are working with. Once we have these raw bursts, we first need to align them, because when the user is capturing a photo, there is always a very subtle handshake. And even this subtle handshake, let's say a misalignment of a single pixel or 2 pixels, can make a lot of difference in how your image restoration network is fusing those frames. So image alignment here is a very critical step. Once you perform your image alignment, you will feed these aligned frames to your neural network, which now has details of your aligned frames and also your camera characterization details coming in. And then this network would just output a good looking image in standard RGB color space, and followed which you can always have whatever post-processing blocks that the user may require for. And this post-processing block can be swapped away with whatever requirement the customer may have. So customers may have a requirement of only needing the output of the neural network and then them using their own post processing, because sometimes these manufacturers prefer to have their own touch of color, like iPhone may have a different aesthetic touch of color than Google Pixel. So at most times OEMs may end up using their own post processing, but the better image quality you get out of your network, better it will progress to your post processing steps. And our neural network here uh, tries to solve for three different problems. Uh, as we already discussed in the traditional ISP pipeline, we have the problem of demosaicing, denoising, and deconvolution. So this single neural network here attempts to solve for demosaicing, denoising, and deconvolution as a joint problem. And until now, we have seen to be quite efficient in solving for all of those at the same time. So before I move to the next slides, I thought it's quite interesting to discuss the problem of image alignment for the use case of image quality, like image restoration. And why I felt that is because how we look at image alignment here is very different than how we treat image alignment in some other use cases. So while I was at Qualcomm, I tried to work on image registration, but that was for the application of 6 degree of freedom. But here, what we noticed was alignment here is very critical in the sense that there are multiple different types of alignment problems that you have to solve for these input raw bursts. Starting from global alignment, which is global registration. Generally, people tend to use some course-based alignment for this. But while you solve for global alignment, you have a lot of local motion in the scene, because a photo that you may capture may have many people moving in it, and let's say a bus moving on the background, a person moving on the foreground. So your alignment here has to be robust enough to solve for both global alignment and also local alignment in tasks such as visual SLAM or visual odometry. Just a few key points are enough for you to start adding it to your map. But here, these key points or these registrations are much more critical, because you essentially need uh, a pixel perfect alignment for your network to fuse these details efficiently. Even a minor misalignment here will affect your neural network significantly. There may be some multi-plane registration requirements here, as I just discussed. Like you may have people walking in front of a bus, so there are two different planes of alignment required here. There may be even more than two different planes of alignment required. So you have to essentially align for individual planes and then you have to merge them and form like a global alignment for that entire reference image. Now these alignment tasks also, like the same alignment module essentially needs to work for whatever light conditions you may have. So you need a good photo, be it bright light, medium light, low light, or even ultra low light. So your alignment procedure here has to be developed in a manner that it is able to attain good alignment, be it any lighting condition. And not only that, as we discussed that these are running in real time, so it has to run very fast. We don't want to, since our entire pipeline is kind of in segmented in two parts. So one is alignment and one is restoration. And a major, like bulky part of this pipeline is the restoration part. So we want to reserve most of our compute for restoration. Hence, for registration or image alignment, we don't have a lot of compute and bandwidth. So we still need a very good alignment, but it should also be running very fast and very efficiently. We cannot use available alignment methods from academia or some classical alignment methods from decades back, because they are either too slow or they are built for a different use case. Hence, we had to develop our own in-house image registration framework. And I'd say we kind of spent huge efforts on making it good for our tasks. Now, of course, there is a possibility that this registration that we have developed may not work that well for some other use cases, but this was heavily trained for the use case that we try to tackle. So some general evaluation protocols that the academia currently tries to follow for the task of image quality assessment or IQA for these image restoration networks can be broken down to these 4 metrics. So what I'd like to show from this slide is that some of these metrics, while being heavily followed in academia, do not correlate that well with how the users may prefer their images to look like. So even if you end up optimizing your neural networks for these metrics, that may not eventually give you the desired result that the user, or let's say the OEM, may want. One very common metric is PSNR, which is peak signal to noise ratio. This is a very classical engineering metric. What it tries to do is it just measures raw pixel by pixel mathematical difference between two images. So you have your neural network output, and then you have your ground truth, let's say. So this metric will just measure pixel by pixel difference between these two images. And the more you optimize for this, more smoother or more closer your prediction will move to your output, to your ground truth. But most of the smartphone makers these days, you can also probably check on your phone later, is they tend to add a lot of grain or a lot of like very subtle noise to your image, and they do that so that your image can look sharper. Because whenever you capture an image, uh, you desire it to look very sharp just on the first go. So in order for you to feel that it's a sharp image, these smartphone manufacturers tend to add some grain onto it. And if you optimize for PSNR, then there is no way you can still end up getting these outputs with additional grain onto it, because your PSNR will never be high for your predictions that may have this grain. A few other metrics such as SSIM, which is structural similarity index measure, it is a perceptual metric, and it is used for measuring the visual similarity between again the prediction and its original ground truth. This is not pixel level, but it just measures the similarity between two images. But we cannot always optimize for SSIM, because as we just discussed, users desire for an aesthetically pleasing image, and what an aesthetically pleasing image may look like is a very brand oriented look. So iPhone may have a very different aesthetically looking image than a Google Pixel or some Asian smartphone manufacturer. So it's very complicated to optimize for these metrics while also sticking to what that aesthetic pleasing looking image is for that manufacturer. And same goes for other like perceptual metrics such as LPIPs, which stands for Learned Perceptual Image Path Similarity, and TOPIC, which is transformer-based opinion-aware image quality metrics as well. So what we found was generally users and manufacturers, they don't want a generically good photo. What they instead want is a photo which looks good to their customers. Hence, it must correlate with a style that that OEM is working towards. Therefore, while training these networks, we have to be very careful on how you eventually converge the network to a manifold wherein it has good details and it also can be easily post-processed with an aesthetic look that the OEM may desire for. Now, there's always an argument that we can end up using some of these state-of-the-art models, which in academia has shown very good, like very high metric scores and very good image quality. But for them to run on smartphone is very computationally expensive, and it is quite difficult to deploy these real time on edge devices, especially on like smartphones. So some of these networks here, such as BSRT, Restormer, Uformer, all of these are quite state of the art in the field of image restoration. And if you look at the size and the rough runtime on a 512 cross 512 patch uh, on a like physical RTX 4090 GPU, it already takes too long. It takes close to like 150 milliseconds. However, the smartphone GPUs that we are working on are magnitudes slower than 4090. And to give a rough estimate on what the runtime should be, so on a smartphone, a comparable network here should run should run end to end on this 512 cross 512 patch in roughly 25 to 30 milliseconds. So it is already in orders of magnitude smaller than it is already in magnitudes like larger than what the requirements are. And these networks are also more complicated to deploy. Hence, it makes it quite difficult to just go and try out the best available networks for your tasks, because eventually the goal is to run these real time, and thus building up like bottom up a smaller network which is more physics aware, optics aware, has proven to be a better decision than going top down with one of these existing academia papers. So in this slide, what I wanted to draw attention to is how we, so since one of our core agenda was also to develop this in a manner that it can be scaled across devices, we really need to develop a procedure which does not need to be tuned per device, right? So what we try to do is we try to break our entire pipeline during development into three stages. One of them is pre-processing, where we do all the pre-processing tasks such as what we discussed, like low-level correction or raw burst collection or any pre-processing that those raw images may require. Then in us, and that can directly be translated to on-device deployment, and most of those deployment is currently done in C++, OpenCL, or using Qualcomm HTTP platforms. Then we train our model, which essentially just transfers to converting those to a format that these phones can use. So we just deploy the trained model and that's it. And on the post-processing, we try again to follow a very similar pipeline as how the pre-processing is done. Hence, for deploying it on device, again, we try to use the same tools, branching out from C++, OpenCL, and QNN. And we try to keep it very modular in a fashion that the moment you get a new camera, you follow the same trained model and post-processing approach, and you can immediately deploy them on that particular device. Of course, there would be some cases where you may not be aware of like what models would end up working on a newer device. Let's say now we want to move to a device which let's say we want our neural ISP to work on a variable which has not been there in market yet. So we would take some time to understand what are the hardware requirements of that variable. But once you have that, your pipeline is as scalable as it was before. So it's very modular in that manner. In the next few slides, I wanted to show some side-by-side comparisons with some of the most recent smartphone we compared with. So in this slide, on the left, okay, so for fair comparison, we always capture the same RAWs. So let's say we capture this photo on Google Pixel phone, and then we use the same set of RAWs and then pass those through our neural ISP block. So it's always a fair comparison. You would not expect differences in image quality because of different RAWs. So these are using the same set of input images. So here, this is a very zoomed in scene of one of the DxO charts, and you can, like, on zooming in, we were able to see a lot of softness in the output of Pixel camera app, which we believe is because it's the softness of optics, which the network was probably not aware of, is adding to this blurry appearance. However, the one on right gives a much clearer image from the same camera. Here we also try to show comparison. So the one here was on a different sensor module. Here we use a very latest 200 megapixel hex mode, like a telehex sensor from one of the Android flagship products. And here we again follow the same approach. And in this example also, you can see the significant increase in clarity our network brings to this macro shot. And we believe smaller the pixels are. So for this hex, the pixels, for this hex sensor, the pixels are very small. So smaller the pixels are, more noisier your input is, and more difficult it is for traditional ISPs and existing pipelines to work well on. And here, the delta of these approaches with our approach increases even more, because our network is able to learn these sensor noise and optical characterization details and is able to revert for those. Thus, smaller pixel sizes we can expect even bigger delta. And the industry tends to be moving in a direction where people want, like, at least these manufacturers want, like, 40x zoom or 100x zoom or even more than that. So in such cases, it is only possible if they start moving towards, like, hex sensors, like telehex, very high zoom lenses, and then these pixels would always get much noisier. So we believe in the future, neural ISP pipelines would be even more widely used. Some more examples from the same 200 megapixel Android flagship, and you'll see a lot of, so I don't know if you're able to see my arrow, but there's a lot of, like, dispersion around the roof of these buildings, which also, like, kind of looks like magenta-ish, and then a lot of dispersion around the boards, and all of these dispersion artifacts are coming because of the optics of the lens. And unless your network is aware of these optical details, there is no way it can correct for these dispersion issues. Obviously, you can always have a post processing block which corrects for these, but then that will be very scene specific post processing, and at times it is very difficult to develop a pipeline which is applying post processing to such niche scene categories such as color dispersion. Here is another example where we see a lot of color dispersion and color noise on this image on the left, which gets corrected when we move to using the neural ISP pipeline that we just discussed. Couple of more examples from the same camera, and it again features the same extreme telephoto module. These results were very motivating for us, because it was also one of the initial efforts that we were trying to work on with these big like hex sensors and very small pixel sizes, and we were amazed to see we are still able to do much, like we're able to perform significantly better than the default camera apps. After going through all these smartphone results, we thought we should also give it a try, because the eventual goal was to scale this across devices. So while scaling across devices, we did the same approach, but this time with DJI Mini 3 Pro. So we On the left is what you would get from the camera app of DJI, and then on the right is what you would get once you use this neural ISP block on top of DJI's input RAWs. And we found that the image quality difference is even more significant on these drones. And our understanding there was, it's probably because the camera teams at these drone companies are not as big as what you would find in a smartphone company. Thus, it is quite interesting to at least estimate that maybe these drone companies are still using the quite classical and traditional ISP approach, and are probably using these images for some other downstream tasks. Hence, the image quality delta here is even significant. To show what benefit we may have by just getting a better software, what we try to do was, there is a benchmark which is related to checking how good your camera is. And so we use the same DxO mark, which generally tells which is the best smartphone in terms of image quality in different areas. What we did was we used a default camera app with one of older Motorola phones. So we used their hardware, and then we just ran it with our own software. So with Glass AI software, these results are from like a year ago, but the idea still remains the same. So once you put the new neural ISP software on top of existing hardware, we saw a huge bump in the overall DxO score from going from 58 to 108. So earlier this phone was ranked somewhere around 87th, and then it went up to 14th, which was even better than Apple iPhone 15 Pro and even Pro Max. So what we were able to understand from this is, even when you have a very inferior hardware, you can still get a very good score if your software is aware of what issues that hardware has. So essentially, you may not always need to keep or continuously investing in your phone's hardware, but parallel efforts in improving software are very critical too. So these are some images from the phone that we just discussed. So this is how, on the left is how it used to look like, and on the right is significantly sharper, not just sharper, but even more details, less blurry, less artifacts in general. So most of the talk until now was focused on still photography. Now we try to apply the same approach and try to apply this approach to video, and this is what we demoed at Qualcomm Snapdragon Summit in October 2025. So I'm playing this video now. So on the left is same hardware as the one in middle. Oh, sorry. Yeah. So the one on left is same hardware as the one on the middle, but middle is when we use our neural ISP block. And then on the right is 3x optical zoom on Samsung S25. So here, what we wanted to show was the hardware on the left is quite inferior to the hardware from Samsung S25, but with our software neural ISP block, we were able to improve the quality so much that it even was better than the flagship S25, which has a different optical zoom. So S25 here, this shot was taken at 3x optical zoom. However, the one in the middle was taken at a 2x optical zoom. So it is already having, Samsung is already having some advantages here, but you'll see very subtle difference of overall sharpness. And even if you look at the water here, the details on the water, the ripples are much better in the one with Glass AI. Even in this scene, so what I try to do is I try to zoom out of this scene to show what the reference scene was, and we still observe similar benefits. So this is again with 2x optical compared with 3x optical on S25, and you'll see here this is a highly zoomed in scene, and first of all there is drastic difference between leftmost and middle, and then the one in the middle is still much better than what we get from S25. So our idea here was very similar to what we have discussed so far. So while using optics aware processing pipeline for video, we are still seeing similar benefits, which aligns well with what our initial first principles of computational photography were.
Shivansh, I just want to do a quick time check.
Yeah.
Because
Yeah.
we are
So,
getting close to the
mhm.
end of the assigned time. I'm wondering
Yes.
how long more do you need?
Oh, this was actually my last slide.
No, okay, yeah.
Yeah. So, so to summarize, through this talk, we tried to set like a new paradigm in computational imaging, wherein we want to propose for a new neural ISP software, which is end-to-end learned neural ISP software. It is uh, it like dramatically accelerates the current development cycles of R&D, so brings down from months to weeks, and then it is so there's a separate line of how we do this that we have on our web page, wherein we also do a lot of research on deep optics, which is different from computational photography. So we draw inspiration from deep optics and try to make our networks be aware of them. And yeah, thank you everyone for your time. Feel free to reach out to me on this email ID if you would have any other questions. Yeah,
Thanks
thanks
so
everyone.
much. It was very insightful. So let's go to the audience to see if anyone has any question.
Mhm.
Okay, so I think I've got two. Is it possible for you to go back to that slide with the bike in which the rear license plate was showing?
Yeah.
It had some characters and some digits on it.
Okay. Yeah. Can you guys see the slides?
Yeah.
Okay.
Oh yeah, I
So
passed it.
this one.
Yeah, this one. So
Yeah.
quick question. So in the original image, there are some digits or some characters that are honestly not much information there to infer
Mhm.
what they are what they actually are. So
Yeah.
I assume that neural network learned some priors from data about which character is most likely to be there, right?
Yeah, it is. So this can be kind of thought as two different directions. So one of them is this image on the left is already quite corrupted because we are not aware of what neural network processing this default uh, Android phone is using. But if you just look at the RAWs may have some details on to what these characters may be. So that prior information is what our pipeline heavily relies on. And then
Yeah.
the one on left also, like these could essentially be generative models, right? These could be hallucinating on these text. So we are not aware of that too. So while we try to restore, we try to stay closer to what the true, like accurate text was meant to be.
Okay. But there are still cases that some prediction may go wrong because given the quality of the original image, right?
Yes, for sure. Yeah.
So the next question comes, okay, this is one character or one digit, but if it's a sequence of characters giving a meaning to let's say, a word or a sentence, do you also check for the semantic correctness of that larger concept? For example, a bunch of characters form a word. Then do you check that whether that word that was reconstructed also makes sense?
Yeah, at this point, our processing is still limited to the receptive field or the context it can work onto, but that is
Okay.
something we are like continuously working on. So we tried the issue we are facing there now is like since these are very compute like specific tasks, for us to increase the context window is becoming like a challenge.
And also, it seems like some problem for also OCR. and how it needs to get fused into the camera pipeline.
Mhm.
And one other thing that I want to ask you about is that, do you generate all the pixels in the original image, or you just try to predict as few and just have a quick workaround to replicate that? I'm asking this question because Jensen Huang, in multiple of his keynote talks, he just say that we either generate only 1% or 5% of pixels, and then the neural network takes care of the rest.
Okay, yeah.
I
Here
think
we,
there he was talking about ray tracing, but I was wondering if similar concepts applicable here.
yeah, that's a very good question. But here, we try to restore all pixels because uh, it's if we just restore few pixels and then just fill up for the remaining, we also move closer to generation task. But since we are sticking with restoration, we try to do it for every pixel.
Yeah, makes sense.
Mhm.
All right, yeah, that was about from my question.
Everyone, can you hear me?
Yeah. Hey, Upal. Yeah.
Hi. So one question. I saw that you tried your the neural ISP on different camera. Did you have to fine tune for each of them?
So there was a very small cycle of fine tuning on that particular camera, but I would say it was a very quick fine tuning, and most of that fine tuning, as we discussed, was more around aesthetics and not so much on the details.
But it would require getting some data.
Yeah, but that
Like,
is like very, very minimal, and I would say those fine tunings could potentially be done in even like 2 to 3 days at max.
okay. No, but I'm curious. Like, are you considering any like test time adaptation technique instead of fine tuning on like all different devices? Because there are like test time adaptation techniques people are always exploring. Have you considered anything like that?
So at present we haven't considered any test time adaptation techniques, but that may be, yeah, I think that may be an exciting, like an interesting approach we could try. We haven't experimented much with that yet.
Okay. Sounds good. I see a hand is raised. Tom, please feel free to unmute and ask.
Hello, this was a very, very informative and interesting talk. I appreciate it. My career had me in the area of lens design for most of it. And I had been, before I retired, pursuing something I called computational imaging, where instead of optimizing a lens for its optical performance alone, optimize the lens, the sensor, and the ISP together to try to not only get a better image, but maybe do it with the cheaper lens. So my question really is there any opportunity for integrating this kind of technology with, let's say, the design process at an OEM, where you might have access to the aberrations of the lens being designed directly? And can that help even shorten this process further from what you've done already? That's one question. The other question is, stray light is a huge problem in some of these systems because they're being used in places where it's not a human being aiming a camera, but the camera is fixed to a vehicle or whatever. And so stray light's coming in from the sun or other sources and putting unrecognizable information onto the sensor. And I wonder if that's also something that you've thought about.
Yeah, thanks, Tom, for the questions. I think both of these questions are very close to what we are facing right now. So the first question about, so regarding the first question, we are currently actively trying approaches on like lens and software co-design. So wherein if we get if we get access to lens aberrations even ahead of getting the device, how we can co-design how we can co-design our system along with those lens properties. So that is something that we are currently working on. An issue that we were facing there was more on the logistics, because for us to get access to this process, we have to first prove why the software process is important in this aspect. So until now we have tried to prove that. Now, since that seems to be like approvable, we are now moving towards co-designing this software pipeline along with Lens even ahead, and that will help us reduce the overall processing time even much faster. And we're also trying to take that to the next step, as in we are also uh, trying to propose some lens designs which we feel would be even better for these manufacturers from the lens designs that they currently have. So we're also trying to propose for those. Then for the second question, we still find quite some issues in highlight recovery, especially on use cases that you mentioned about, like lights coming straight into your lens and then falling onto the sensor. So we that still seems to be an unsolved problem that we have currently, but we feel generally on highlight recovery our process is already more advanced than what we see on default camera apps.
Are you open to me introducing you to people at the company that creates Code 5?
Oh yeah, sure. I would love to get in touch.
Maybe there's some opportunity there. I don't know.
Mhm.
One more thing. Are you willing to share your slides?
Yeah, I can. Yeah, I'll try to trim
I
down
didn't
some
see the
details,
word
but
proprietary on anything, so I just wanted.
yeah, I think it should be good. I used,
Okay.
yeah, most of this should be. Yeah, I'm happy to share the slides. I'll get in touch with Pirash to work on the
Yeah.
logistics.
So once we get the recording, we are going to post on our YouTube channel, and there we'll provide a link to the slides as well.
Okay. Yep.
I also see Aditya has a question, and next is Jean. Okay, so Aditya,
Yeah.
do you want to ask your question?
Hey, hi Sivansh. It was a nice talk. So, if it is okay to share, like, what is the underlying model for the ISP, like the neural ISP, right? Is it a
Yeah.
diffusion-based model or any other generative model that you guys
Mhm.
use? Like, maybe at high level, if you can give some insight into it, if it's possible. Yeah.
That's a very good question. So right now, if I would have to share high level, so we are still trying to, and by we, I mean like not just glass, but also like some smartphone manufacturers in US that we may be aware of are still trying to stick with the restoration, like simple convolutional based models, and uh, have not started using diffusion models for like their main cameras and telecameras yet. But there was, I think it was in Pixel 10 Pro, where they had a demo showing their 100x zoom. That I guess is probably the first smartphone in US which ended up using diffusion. They also kind of claim it in their blog post on Pixel 10 Pro, but they are currently running diffusion model on the cloud. So they capture the image and then they send it to the cloud, and then they run the diffusion there, and then they process it back. So I think for diffusion on device, I'm not sure if it's still there in the market yet.
Yeah, got it. Yeah, thanks.
Mhm. Yeah, thanks, Aditya.
We also have Jean with a question.
Yeah. Yes, very good talk. Thank you. I did have a question. On one of your slides, you mentioned some of the difficulty in translating PyTorch to OpenCL plus QNN.
Mhm.
There's a lot of work going on now with what I call much higher level code, you know, that tools like Claude with Anthropic are writing code. Does that apply at all in your area? Can you get assistance in that kind of translation, or is that still way beyond?
Yeah, I think so we have tried to use as much of it to our best interests, but for tasks like OpenCL, kernel coding, and QNN conversions, we found it's definitely useful, but we have still found ourselves ending up spending a lot of time on debugging these uh,
Okay.
things at present. It has definitely been very helpful for research, but for these deployment related tasks, it's still in a state where we cannot use it as it is. There was a recent blog post I saw on how Anthropic coded up the C kernel compiler with like 16 different agents, but we haven't tried that yet. So I don't know about that.
Good. Okay. That's good to know.
Mhm.
Say, I had a kind of a funny question. So I had a cataract operation, and they put lens in that corrected my astigmatism.
Mhm.
But there are modes where I can put my eyes where I'll get some reflections and some aberration. Do you see technology like you have eventually being able to correct that type of thing? It's a little different, but it would certainly be useful, right? So
Yeah, I think from technology point of view, in
yeah.
principle, it should still be correctable, but from business point of view, I don't know how scalable it is.
Yeah. Well, it's probably a little out there yet, but thank you. Anyway, this is very, very good. Do you have any references you can recommend if we're not too familiar with this field?
Yeah, for sure. So we had a whole tutorial on this recently at ICCV 2025 conference. Uh, I can also maybe pass that tutorial detail to Piraj. And it was, so we gave a talk there, but it was also it also had people from Sony and other camera related companies. So they had a lot more prior information and also most of the work that they are doing these days. So I can also share those details.
Yeah, that would be great if, when you guys post your stuff, that would be helpful.
Mhm.
Thank you.
Yeah, for sure.
All right. Great. Do we have any more questions from the audience? If not, thank you so much, Shivansh, for your very interesting talk. I really enjoyed, and I think you can tell from the Q&A session.
Yeah, thanks.
Yeah.
Thanks, Biraj. Yeah, thanks, Upal. Thanks, everyone.
Yeah, thanks, Shivansh. It was very nice. Thanks.
Yeah, thank you. See you. See you
Thank
again.
See
you.
you. Bye.
Bye.
Thank you, everyone.
Bye-bye.